And so we've taken a quick look at what dyslexia is, the literacy aspect of it, that dysfunction, again another deficit, unfortunate word, with being able to engage with the printed word, that relationship in between sounds and print. And now for, I think, a clearer perspective, we can get a clearer perspective from neuroscience. And for this, we're looking at the work of Mello and Gabrielli. And references, of course, for all of these you'll find at the end of these slides, references for the various knowers that I refer to in this webinar. And so according to Mello and Gabrielli, dyslexia results from differences between the building blocks necessary for learning to read and the regions in the brain that support these building blocks. Causes of dyslexia are not known. It's seen as heritable, and therefore dyslexia is likely to run in families. And from a genetic point of view, there have been no links found as yet, or as of the time that they published, no specific genes have been found between reading abilities, dyslexia, and any genetic code. 5 to 17% of children are estimated to have developmental dyslexia, and of course dyslexia in the brain will be found on the left hemisphere in the same way as where you would expect to find it, because the left hemisphere of the brain houses those parts that deal with language and reading. The parts of the brain, in this sense, are referred to as cortices. And these three cortices, there are three cortices that form a neural network, referred to as the reading network, because these cortices relate to reading ability when they're activated. Mello and Gabrielli did a lot of their work that is refers to in this webinar was done through MRI research, and cortices in the brain were observed for their responses to a variety of literacy and reading activities. So the cortices are all on the left, as mentioned earlier on. We use some medical terms here, which this is an education webinar, so I'm not going to make a habit of pronouncing these words, but just to start off with, the three cortices referred to are the occipitotemporal, I'll refer to this as the OT, the temporal parietal, I'll refer to this as the TP, and the inferior frontal, I'll refer to this as the IF. So the left OT cortex is also known as the visual word form area, and this area is activated when sounds are represented in visual form through printed symbols or words. So if we have a think about that, this part of the brain referred to as the OT cortex, and for us laymen we can also see it as the VWFA, visual word form area. So in this part of the brain, the formation of printed word takes place. Is almost as if the brain, in quotes, in layman's language, can see the words in that area, the visual word form area. And this visual word form area represents sounds, the sounds of that language. And so you make a sound, or you have a joining together of sounds to form a word, and that word now resides in the visual word form area. People who have damage to this part of their brain can lose the ability to read, and so they could have been fluent readers beforehand, have an unfortunate accident, and when the VWF area is affected, it affects their ability to read. It can be argued that the development of the VWFA relies on both the physical state of the OT cortex and the educational experience of learning to read. This is quite interesting for us as educators because, of course, as we know, education is a social experience. Learning is a social experience, and there could be various factors that take place within the education setup that is presented to a learner when they're learning to read. And this also contributes to how the VWFA forms. So if we're bearing in mind that the brain is plastic, the brain has plasticity, cancel the plastic aspect. It has plasticity, and what that means is that it's fluid. The brain develops and moves and is malleable. And so in carrying out a particular activity, certain parts of the brain develop. And that, does really have a lot of implications for the sort of educational environments that we provide for learning in general, and in this instance for learning to read. So the ability of the verb word form area to respond to print is there at the pre-reading stage. So the ability is there. And the ability to respond to specific printed words now develops over time. So your typical learner comes with the ability to respond to print. That is already there, and at the pre-reading stage. And as they respond to print, that now develops. The response develops, and of course the word form area develops, and you can see that in their ability to read and also to do so fluently. And so that's on the OT. Now, the second area we're going to have a look at is the temporal parietal, the TP, which I'm going to refer to as TP for ease. So the left TP cortex, again, we're talking about the left side of the brain, deals with cross-modal integration. And what that means is you have different modes of engagement as a physical individual. And when you have two modes integrating, you have a cross-modal integration or cross-modal translation. So for example, you have visual print being translated into audible sounds. That is what happens when you read. At the moment, as I'm talking at this webinar, you're probably having a look at the slides, or you're probably having a look at something else. You might be reading a text because you find this not too exhilarating. But by looking at that print, that is the visual print is one mode, and then if you're reading out aloud, that's being translated into audible sounds. If you're reading it inaudibly, but there's still some internal conversation taking place about what what's being read. And so that is an example of cross-modal integration, a translation from the sight of a printed word into a sound that print represents. In general, learning to read usually starts with spoken sounds. Children learn to speak first before they learn to read. And we have proponents that argue that reading is actually an unnatural skill that we develop. Children learn to speak. We don't teach children to speak. They come genetically packaged to be able to speak. But we need to be taught to read. If you're not taught to read, you would not know how to read. And so that's synthetic. And there is, I think, a strong basis for that argument. Having said that, the brain is able to take on this synthetic skill, as we've seen. It's got that space there, and therefore people do learn to read. So learning to read starts first of all the spoken sounds. Those sounds they make sense to the person who's learning to read. The sounds are heard, and from those sounds meaning is made. And so when you hear sounds, go, stand, you say to a child, hear, smile, happy, whatever sounds that you make, the child is able to extract meaning from those sounds, because those sounds form the language of that particular culture. And for as much as a child is from that culture, they would extract meaning. So this is phonological awareness. Sounds are heard, and then when it now comes to reading, these sounds that are heard, that the child is able to make meaning from, and probably even to speak, get mapped onto print. And of course, we're talking about the brain, that will take place in the verbal word form area. So the left TP cortex deals with the development of the phonological skills necessary for reading. And as I mentioned earlier, it's cross-modal. Those phonological skills are the sounds and how those sounds are mapped onto print. Now, the third area is the IF, the inferior frontal cortex, and left part of the brain, and it's prominent in dealing with the reading and development. And this is associated with verbal working memory, phonological processing, semantic processing, reading silently, and speech production. Verbal working memory, of course, is that you're able to give out a number of instructions or a string of words are said, and the hearer has a short-term working memory which holds that instruction in order to be able to respond to it. It also deals with phonological processing, as we've mentioned earlier on, which is the ability to recognize sounds and to extract meaning from those sounds. That brings in the semantic aspect of it, whether you're reading silently. And we've also spoken about the production of speech. And so, as you can see, there is overlap, if you like. There are connections in between these three cortices. And the three cortices, the OT, the TP, and the IF, work together with the auditory and visual regions of the brain to form a neural network which develop and sustains reading behaviors. Now, it's important to note that there's coordination and connection between the different cortices in the neural network, and this neural network is called the reading network. So the connections and coordinations between the OT, the TP, IF, and any other parts of the brain that are drawn on for reading form the reading network. So typical readers will have a high volume of grey and white matter in their reading network, and also strong white matter connections. I don't know how much people know about the brain, but you probably will be familiar with layman's terms. You hear things like grey matter or the grey cells, these are groups or collections, if you like, of neurons through which form the brain, and of course which carry messages throughout the brain. And of course, where you have a denser collection of the neurons, you're more likely to have greater activity to do with the area that is represented. And so in the reading network, for example, which is to do with sounds, with the recognition of printed material, connections in between the sounds and the printed material, and the other areas that we've discussed, the higher volume of grey and white matter that you have in those areas, the stronger the activity is likely to be. White matter, you might want to read that up, and it's to do with the movement of electrical circuits across the brain. And of course, the quicker what the white matter does is it enables those electrical impulses to move a lot quicker at a greater speed. And what the white matter does is make connections in between the different cortices. So I'm not a scientist, so I'm not going to say too much more about that. I'll leave that to the experts. And so the differences in the structure and the function of the brain's reading network is where dyslexia comes in. Because it's associated with these differences. So what we've spoken about so far is what you would typically have in the development of a reading network in your typical learner's brain. Where you have differences in the structure of each of these cortices or in how they function, then you would you begin to engage with dyslexia. So if, for example, there's impaired phonological awareness, then obviously there will be issues with reading. And the dyslexia is characterized by an impaired phonological awareness. So activation in the reading network comes with increased effort in reading. Dyslexics, however, show differences of underactivation when it comes to phonological awareness. And the difference of underactivation has been shown in the VWFA, the verbal word form area, and it's also been seen, underactivation has also been seen in the TP, that is the temporal parietal part of the brain, that cortex, where you have the cross-modal connections. If you remember, you have cross-modal connections, integration, whatever you want to call it. And in this instance, it will be in between the grapheme and the phonemes. So phonemes, of course, are individual units of sound, and graphemes are individual units of print, which is a visual form of that sound. And what Mello and Gabrielli found in their work was that there was underactivation where you have the grapheme phoneme connections, or the grapheme phoneme mapping. Even where there was increased effort, there was still underactivation. Interestingly enough, with the OT and with the TP, there was underactivation for learners with dyslexia. However, with the IF, there was hyperactivation. And this has been explained as overcompensation or compensation. So where, because there's underactivation in the other two cortices, the IF looks to carrying out compensatory measures in order to get the learner to be able to read. And so what they noted through the MRI scanning was that there was hyperactivation in the IF when you had underactivation in the other areas. Right, so, and this probably might sound a bit complex. Hopefully I haven't lost you. But where there is impaired phonological awareness, another thing you would also see are challenges to fluent reading. So if we take a look at those two, because reading, of course, is about phonological awareness and fluency. If we just look at the technical aspects of reading, of course, at the secondary level, meaning comes into play. But even if we're just looking at those primary aspects of it, where there is impaired phonological awareness, it is possible to carry out remedial activity in order to deal with this, and we'll have a look at this in the next slide. However, where there are problems with fluency, this is a lot more difficult to remediate, and maybe with a bit more research, we would know how this can be done. But where there's a diagnosis of dyslexia, both the phonological and the fluency abilities are considered for us to know whether or not this is dyslexia or it is a different issue with the reading ability. And one thing that is important to note, and Mello and Gabrielli noted as well, is that dyslexia and IQ are independent of each other. There have been many people with high IQs who have difficulty, who have had dyslexia, and so there is no link between those two areas. And so if we take this to the classroom and have a look at mixed ability teaching, and then we'll now link this to what we've been talking about to do with dyslexia.